Dear students, I welcome you all for today's session on electronic devices and circuits. See, in the last class, we discussed how a transistor is working as an amplifier. Today, in this class, we will discuss what is transistor biasing. We will discuss the concept of DC operating point, then DC load line, AC load line, and how we draw the load line of a transistor. Okay, now going to what is transistor biasing. You know that in a diode circuit also, biasing means the process of applying an external voltage. Okay, so in transistor circuits as well, we apply an external voltage source to establish a fixed voltage and current in the circuit. Okay, so in transistor applications, sometimes this transistor has to be operated in the active region, and in some applications the transistor may be operating in saturation or cutoff regions. So in order to bias the transistor in the required region of the operation, we have to apply an external voltage. Okay, so and there is one more point why we go for biasing. If the transistor is configured as an amplifier, for the signal to be faithfully amplified, the transistor has to be properly biased. So whatever be the transistor circuit, to obtain the desired characteristics, we have to apply an external voltage, or we have to bias this transistor properly. Okay, now here, so by applying a bias, an external bias, the circuit establishes some fixed values of current like IB, the base current, IC, the collector current, then base emitter voltage VBE, and the collector emitter voltage VCE. So these are the values of voltages and currents which are very important. So the fixed values of these voltages and currents are called the operating point of the transistor. Okay, so if we look at the characteristic curve, the output characteristic curve of a common emitter transistor amplifier, we know that we plot VCE on x-axis and the collector current IC on y-axis. Okay, so this is the set of curve that we obtain when the transistor is configured in the CE configuration. Now, when the value of VCE is equal to 5.7 volt, you can see from the graph that the value of collector current is 20 milliampere. Again, when VCE is 3.5 volt, the value of IC is 30 milliampere. So this point on the curve defines a point Q2, and this point on the transistor cara defines another point Q1. Similarly, when the value of VCE is somewhere here 1.2 volt, when IC is equal to 40 milliampere, the point we obtain a point Q3 in the characteristics. Okay, so we have 3 points Q1, Q2 and Q3 in the curve. So if we join these 3 points, we obtain a line called the load line of the transistor. Okay, so these points Q1, Q2 and Q3 are known as the Q points, or the quiescent point, or also called as operating point, DC operating point. So see here, the term quiescent means the point is fixed, still or inactive, or it is quiet. Okay, so there is a very important concept here. So after biasing and after fixing the Q point need not or should not change. Okay, so here these fixed values of voltages and currents establish a point on the operating characteristics, and we call these points as the Q point or the DC operating point. Okay, and the Q point is obtained when no input is applied. We are not applying any input AC signal to the base. So we are applying only a DC signal to bias the transistor. Okay, so we are not applying any input AC signal, but we are applying only the bias voltage. Okay, so it establishes these points on the curve Q1, Q2 and Q3. Alright, so if we join these points, we get a straight line, and this straight line meets the x-axis at a point known as the cutoff point. Okay, so this is the cutoff point, and the line meets the y-axis on a point known as the saturation point. Okay, I will explain in detail what is this cutoff and saturation point and how do we obtain this. And the region in between these cutoff and saturation points is called the active region. Okay, so this is, just follow the cursor movements, listen. See here, in this region, the transistor is acting or behaving in the active region. Okay, so for any amplifier application, the transistor has to be working in this active region. Okay, to configure the transistor as an amplifier, the transistor has to be operated in this region. Now, imagine a switch. If the transistor is configured as a switch, the transistor should be working in between this cutoff and saturation. That is, it is switching between cutoff regions and saturation regions. Okay, so that is the importance of these three regions. So to configure as an amplifier, the transistor has to be operated in this region, and to configure the transistor as an electronic switch, it must be operated in saturation and cutoff regions. Okay, so I hope you understood what is Q point, what is load line, and what is saturation point, then active region and cutoff point. Now, so we can see here, so this is another graph that represents the DC load line. So the DC load line meets the collector current or the y-axis at a point A, and it meets the x-axis at a point B. Okay, so we can draw this load line from this circuit. So this is a transistor circuit to obtain this characteristics. See here we can see we are applying an external voltage to bias this transistor. Okay, so VCC is the external voltage applied. So this VCC will be equal to, so there is a correction in this circuit diagram, this must be VCC. Okay, so this VCC is equal to ICRC plus VCE. So we are applying Kirchhoff's current law, Kirchhoff's voltage law over here. So if it is VCC, VCC will be equal to ICRC plus VCE. We are considering the output side only. Okay, so VCC will be equal to ICRC plus VCE. You know that when your transistor is on, when the transistor is on, the value of VCE will be, so when a transistor is on, you know that the collector current is maximum, IC is maximum, and VCE will be approximately 0 volt. Okay, or the transistor is acting like a short circuit. When it's a very important concept. When the transistor is on or in saturation, the transistor is acting like a short circuit and the collector current IC will be maximum. Okay, so under this case, if we apply VC equal to 0 here, we can calculate the value of IC as VCC by RC. Okay, so this point A corresponds to the value of IC when it is maximum and when it is VCC by RC. Okay, so this is the saturation point. So in saturation point, the collector current will be maximum. The transistor is just behaving like a short circuit or a closed switch, in which VCE will be equal to approximately 0. So IC will be VCC divided by RC. Okay. Now let us see how we obtain the point B on the characteristics. The point B can be obtained by assuming the transistor is in cutoff region. Cutoff means both the emitter base and the collector base junctions are reverse biased. The transistor will not be conducting and IC will be 0. Okay, so in the previous case we considered IC as maximum and VC is equal to 0, and here we consider IC equal to 0. Okay, so IC 0 means the transistor is not conducting, the transistor is behaving like an open circuit. Okay, this region or the transistor is just behaving like an open switch. So whatever be the input voltage, this input voltage VCC will drop across this open switch. Okay, so if you are applying a 10 volt VCC supply, all the 10 volt will drop across this open circuit or open switch. So if you substitute the value of IC equal to 0 in this equation, we get VCE is equal to VCC minus ICRC, or VCE will be VCC. So that is what I said. In the cutoff region or in the cutoff state of a transistor, the transistor will be off, the collector current will be 0, and VCE, the voltage drop across the collector and emitter, will be nothing but the input supply voltage VCC. Okay, so to understand the working of a transistor or to analyze a circuit, we are applying these techniques. I repeat, if we are considering the transistor is in saturation, we assume the transistor as a closed switch. So IC will be maximum but VCE will be 0. But when we consider the transistor in cutoff region, we assume that the transistor is off, the collector current is 0, the transistor is behaving like an open switch. So all the input voltage will be appearing across the transistor, all the input supply voltage. Okay, and we can see that we are not applying any input AC signal over here. We are analyzing the circuit only by considering the DC supply VCC. Okay, so we are not applying any input AC signal. So this is the point A, we call it as the saturation point, and the point B is called as the cutoff point. And the region between these points A and B is called the active region of the characteristics. Now, this is the same diagram as I explained. So this is point A, the saturation region where IC is VCC by RC. And this is point B, the cutoff region, the transistor is fully off. VCE will be equal to VCC. Okay, in saturation region, the transistor is fully on. So the points in between A and B, I have 2 points P and R over here. These are some Q points on the load line. So this is the load line. The load line is connecting the saturation point and the cutoff point. Okay, so this is connecting these 2 points. So in between we have lot of intermediate points. We call this as the Q points or the DC operating points. And the points between A and B or the region between A and B is known as the active region. Okay, so in order to bias or to configure the transistor as an amplifier, the transistor has to be operated in this region or active region. Okay, so this is what is about the DC load line and the operating point. Now we will discuss what is AC load line. So suppose we are applying an input AC signal here. Okay, we are applying an input AC signal, a sine wave or a square wave is applied here. Assume a 100 Hz sine wave signal is applied here. So the DC load line, the load line that is obtained after the application of an AC input signal is called the AC load line. Okay, so it is the load line that is obtained after applying an input AC signal. So we can see here, so this is the previous DC load line, this is the DC load line. Now the AC load line has shifted somewhat to the right. Okay, the slope is something different. The AC load line and DC load line will not be the same. So DC load line means we are not applying an input AC signal. Okay, but AC load line is the load line that is obtained when an AC input signal is applied. Okay, they are not the same, but a very important point, these two load lines meet at a point known as the Q point or the quiescent point. So this is the Q point of this particular transistor. Okay, so both the load lines will intersect at a point known as the Q point or the quiescent point. Next is, so what is the significance of this load line, whether it be AC load line or the DC load line? What is the significance or why it is so important? Okay, so this we can understand from the next concept, the concept of faithful amplification. Okay, you know that the process of increasing the signal strength is called the amplification. For example, if the input of the transistor, we are applying a 1 volt signal, and if we are getting a 100 volt signal, we say that the transistor is an amplifier. Okay, the signal strength is increased. Now, the concept of faithful amplification means the signal strength or the improvement in the signal strength. The process of faithful amplification is obtaining the complete portions of the input waveform, okay, without any distortion. So whatever be the input signal we are applying, the signal undergoes amplification without any distortion or without any change in its wave shape. Okay, so for faithful amplification of the signal, the Q point has to be properly selected. So while we design a transistor circuit, the Q point should be selected in such a way that it amplifies the signal faithfully. That is, the signal is not distorted. There is no distortion in the output waveform. So as I said, it depends on the position of the Q point in the load line. So we will consider 3 cases. We consider 3 different positions of the Q point, and we will analyze what happens to the input signal if we are selecting 3 different points on the load line. Okay, so the first case is the point is selected near the cutoff point. So this is the cutoff point of the transistor. I want all of you to draw these diagrams. Okay, when you watch the video, please draw all the circuits. Please write down the important points. And if there is some derivations, equations, please note down, kindly note down this. Okay, so here we have the Q point somewhere here. This is the cutoff point. We are applying an input waveform. So if you project the input with respect to these points, so this is the reference point, the Q point is here, we can say that some portion of the positive half cycle is getting clipped. Okay, that is, some portion of this positive waveform is getting clipped. So we are getting a distorted output waveform if the Q point is near the cutoff point. Okay, so in cutoff point, if the Q point is near the cutoff point, the positive half cycle of the input waveform will be clipped. Okay, so it's very important. Next, let us see what happens if the Q point is near the saturation point. So near the saturation point, so this is our Q point. Q point means at this point, this will be the collector current and this will be the VCE and this will be the base currents. Nothing but certain values of collector current, base voltage and VCE. Okay, so if in the second case, the Q near the saturation point. This is the saturation point. So we are selecting the Q point here. This is the input waveform. In the negative half cycle, the waveform is getting clipped. So a portion of this waveform is getting clipped. So this is beyond the reference line. So we can see here this is getting clipped. So we are getting a distorted output waveform. Okay. So when the Q point is selected near the saturation region or saturation point, the negative half cycle will get clipped. So let us see if the Q point is selected halfway or midway between the saturation and the cutoff points. So this is our cutoff point and this is the saturation point. So in between these 2 points or halfway between these 2 points, the Q point is selected. Now this is the input waveform. So from the output waveform, we can see that both the half cycles are preserved, or the signal has not distorted, or the signal is faithfully amplified. So this is a very important concept. That is, in order to configure transistor as an amplifier or to operate the transistor as an amplifier, the Q point must be halfway or midway between the saturation and cutoff points. Okay, so midway between these 2 points means the value of VCE will be equal to VCC divided by 2. Okay, it's very important. So if we are applying a VCC of 10 volt, the VCE value must be VCC divided by 2 or should be 5 volt. Okay, only then the Q point will be midway between the saturation and cutoff points. Okay, so this is very important. So to configure the transistor as an amplifier, the transistor has to be biased midway between saturation and cutoff points. Okay. So in both the previous cases, if the point is selected near the cutoff point or if the point is selected near the saturation point, the waveform or the signal undergoes some kind of distortion. So the wave shape is not preserved. So the signal will not be faithfully amplified. So to faithfully amplify the signal, this operating point must be fixed in between or halfway between saturation and cutoff points. Okay, so these are some factors for faithful amplification. Of course, the first and most important point is the Q point must be halfway between saturation and cutoff point, or VCE should be equal to VCC divided by 2. Okay, and the values of IC and VBE also determines how the signal is faithfully amplified. Okay, so I hope you understood what is load line, what is Q point, what is saturation point, what is cutoff point, what is active region, and how we bias the transistor and the amp as an amplifier, and what are the factors that affect faithful amplification, and what happens if the Q point is selected near the saturation point or the cutoff points. Okay, so I will give you an exercise question. So here I am considering an amplifier circuit where VCC is equal to 10 volt. Okay, so I want you to calculate the value of VCE when the transistor is working as an amplifier. You can send answers in the Google Classroom. You can post your answers in the Google Classroom. Okay. Thank you.